So we're talking about OpenMP and hybrid programming, okay? So we'll talk about the motivation for using hybrid programming, things that we need to think about when we're doing it. MPI threading support, designing hybrid algorithms, and some examples. Okay, so multi-core architectures are here to stay. We have if you think about it, when you think about like a machine like Perlmutter, so we have multi-core nodes, and then we have thousands of those, right? So on the macro scale, it's like a distributed memory architecture, so it's perfect for MPI. On the micro scale, within each node, we have multiple cores that all share memory. And so that is an SMP architecture. So that's perfect for OpenMP. So why not do this? Use OpenMP within your nodes and use MPI between all of the nodes. And so that's what we call a hybrid programming model, because it's using both of these parallelism paradigms. Okay, so now that you're convinced this is great, but is it always better to do it this way? And the answer is no, not always, especially if you program it poorly. And so it depends really on the suitability of the architecture and of the way that you are doing your algorithm. So if you think of it as kind of like an accelerator model, in the parallel region, we're going to use the power of multi-cores, and in the serial region, we're going to use only one process. And so if your code can exploit this type of parallelism a lot, for again, a lot is kind of a subjective thing, then try hybrid programming. If not, don't worry about it. Okay, so here are some things to think about when you're going to write your hybrid parallel program. And there's no right or wrong answers to any of these. It's just things you need to think of. So think about the parallel programming model. Is it going to work? Are communication and computation discrete phases of your algorithm? It's okay either way. Just have to think about whether it is. Can communication and computation overlap, or do they already overlap? And then when we're thinking about the communication, how do we kind of want to do our communications? Do we want to communicate only outside of OpenMP regions? Do we want to have like a manager thread that could be responsible for all communication between MPI processes? Do we want to have, let some threads perform this communication, or do we want like all of our threads to communicate with any other threads on any other process? So those are just questions you want to ask yourself. I mean, typically the simpler the better, just in terms of getting it right. But yeah, maybe you could do a really complex thing and it would be really great. Who knows? So starting from the MPI 2 standard, there were 4 threading support levels. So the 0th one is MPI thread single, and that means only one thread allowed. So that means if you're in an OpenMP parallel section, you can't use MPI basically. Okay, so then the next one is MPI thread funneled, and in this one, the primary thread is the only thread that is permitted to make MPI calls. Okay, and then in the next one is MPI thread serialized, which is like all threads can make MPI calls, but only one thread at a time. So they have to just do it one at a time. And then there's the last one is MPI thread multiple. There's no restrictions. You can do what you want, as my stepmom says. But yeah, anyway, that can be dangerous. So I'm just letting you know. And then if you don't use MPI 2, the MPI 2 standard, if you're just still on MPI 1, if you're not at 2, 3, 4, 5, then you just can't do MPI calls inside parallel regions, which is the same equivalent as MPI thread single. Okay, so then you might want to ask yourself, well, what threading model can I use on this particular machine? So this is a little code that you could just copy and paste into your terminal, and you could compile it and run it, and you would find out what threading model your machine supports. Okay, so the big thing here is this MPI init thread. And these are the arguments to it. And so I'll explain this in a minute, but I did this on Perlmutter. I made this from my code that I did an interactive job. I ran it, and it supports level 3 of 0, 1, 2, 3. So that means that Perlmutter supports MPI thread multiple. Okay. So what is this function that I showed you? You remember when we did our other programs, we did MPI init, right? This is MPI init thread. And so it's similar to the other, but what it's asking for is required. So what is it that you need, that you're asking for? And then this is what it's going to give you back. Okay. And so what it gives you back ideally is going to be what you ask for. But if it's not available, it's going to return actually the lowest level greater than required. And if it can't give you that, then it's going to give you the largest level less than required. That seems kind of odd, I know, but I guess if somebody had like 0, 1, and 3 in their MPI implementation, don't know why they would do that, but if they did, and you wanted 2, then it'll give you 3. Okay, anyway, seems weird, but that's how it works. So if you use just plain old MPI init, like we did in our previous examples, that's going to be the same thing as just saying that required equals MPI thread single. So you won't be able to use MPI within threaded, within parallel regions that are using OpenMP. Okay, and then at the end of your code, you're still going to call MPI finalize, but you want to make sure that it is called by the same thread that called MPI init thread. So, okay, then there's some other useful functions that would come in handy when you're in this hybrid world. So MPI is thread main. So this will return a true false, basically, of whether you're currently in the main thread. And then this one here, MPI query thread, a thread can call this to query the level of thread support for your MPI. Okay. So let's say that we're doing the single model. So if we're going to do that, then we can use just the single pragma for it. So we're going along, we're doing our parallel stuff. We put in a barrier here to get everybody to this point where we're going to use single, and then we're going to do it. And then after that, we have another barrier where everybody's going to wait until that single thread completes and this function MPI XYZ, whatever it is. Okay. If we're going to use funneled, okay, so this is supported for us. You want to use the masked pragma, and so that only the primary thread will execute it. So again, it's a similar thing. We have a barrier, we use masked, and we do this MPI call, and then we have another barrier, and then we continue on with our business. Okay, if we're doing serialized, then we are going to want to use the single. Okay, so we're going to do a barrier, we're going to use single, we're going to do our MPI thing, whatever we're going to do, but you don't need a barrier at the end. Okay, so, okay, I think I needed to update this slide and I didn't. So our implementation actually does support multiple. It used to be that the Cray MPI did not, but nowadays, yeah, it has it turned on, but they have some disclaimers that the performance could be suboptimal. So we don't need any pragmas to protect our MPI calls. We can just put them in there wherever we want to. But there are a few constraints. So the ordering of the MPI calls is going to be maintained within each thread, but not across MPI processes. So you are responsible for preventing race conditions. Does everybody know what a race condition is? No, yes, no. Did somebody put one in the chat? Yeah, no, and a yes. Okay, and a yes. All right, would somebody like to explain race conditions? Anybody? One of you folks who said yes?
Two functions write to the same piece of memory, try to write to the same piece of memory at the same time. And like, say, if you want to iterate something, they may like actually race each other as opposed to waiting until the write is completed and the actual value has been returned to then like add some plus equal to the next value may not actually be referencing the value because there's two things trying to both simultaneously like operate on some piece of memory. Sorry, that was not great.
Okay, yeah, no, that was good. That was an example. That's a good example. So Ron wrote finishing after somebody needing your result starts, right? That's another good way of thinking of it. So basically it's something where, yeah, the instructions taking place out of order adversely impacts what you're doing, basically. So, that's basically a summary of what it means. So, yes, another way to say that is what Anupam wrote in the chat. The order of instructions being executed affects the result. Good. Okay, so anyway, in this multiple, you could, because there's just so many different kind of levels of parallelism that are going on there, it's possible that things could get kind of confused or like things could go in a different order than you were kind of expecting them to go. And so that is a prime setup for race conditions. Okay, so ideally when you parallelize something, right, we've talked about this, it should not matter what order those operations are executed in, right? It should all still work. But sometimes people think that something can be parallelized when it really can't. And that's what you tend to run into with one of these algorithms that is using a hybrid because it's just so complex with the multiple. Okay, so I would really honestly, in my opinion, multiple is rarely required, and most algorithms can be written without it. And so my advice would be to not use the multiple threading model, but to use a lower one, just to eliminate the possibility of maximum confusion in this free-for-all. Okay, so question people often ask me is like, well, which threading model should I use? I give you the answer of a resounding, it depends. So it depends on your application. So the nice thing, I just kind of put down the models and kind of what their pros are and what their cons are. So with single, the nice thing is that every MPI implementation will support single. A con of that is you have kind of limited flexibility in how you can write your program and what you can do. So funneled is also good. It's pretty simple to program. But your manager thread could get overloaded if you're sending out a lot of messages. Serial is also good. You have this freedom to communicate, but they are kind of all waiting in line to communicate, and you also run a risk of too much cross communication. Multiple, it is allegedly thread safe, completely thread safe. It's something that I guess it's not as much limited availability nowadays. I mean, it's pretty much available everywhere. Personally, I think it's something that is also really hard for them to test to be sure that it really is thread safe. And so you could run into some of those kind of corner cases where it's not exactly thread safe. And sometimes it can have suboptimal performance. And like I said, most of the time, the vast majority of the time, you can write it in any of these other models, and you don't really need multiple. Okay, so something to keep in mind is that just because you can communicate thread to thread, doesn't mean that you should, right? It's kind of one of these things like if you're, like your mom probably said to you, you know, all your friends were jumping off of a bridge, would you jump off of a bridge too? Well, she was right in some ways, you know, just because you can do something doesn't mean that it's a good idea. And so you have kind of a trade-off also between lumping messages together and sending individual messages. So if you think about sending messages, right, there's going to be an overhead associated with that, right, because it has to get delivered, sent. And so if you send one big message, you just have one overhead and it gets sent, right? On the other hand, if you send individual messages, each of them is going to have its own kind of overhead to it. However, there could be an advantage in that there could be less wait time. So if I have a bunch of stuff I need to send over and I gotta wait for you to bring your stuff over so that we can send it together, right? Then I'm waiting for a while when I could be computing instead. So there could be some advantage to sending individual messages. It just kind of depends on how you're gonna do it. Another thing to think about is programmability. So we're getting into, it's a pretty complex parallelization. And so you really have to think about it and make sure that that you program it correctly. So that can be a big challenge for people. But once you get it working, you know, the performance will be great. So I'm going to give you a simple example. And again, this is just a conceptual example. There's no code involved. But a pretty common application that we see is a mesh of finite elements. So this is something that people use to approximate something on a domain like the potential energy or, you know, something like that. And a lot of times when you're writing these types of algorithms, you're solving some sort of differential equation. And what we do is we break up the mesh that represents our domain that we're solving over. We break it up into pieces, and a lot of times the value of the function, like the potential energy, let's say, at a particular point is a function of the value of the potential energy at a bunch of points, right? The ones that are all around it. So at these borders of the domain, that's where we're going to have to communicate. So we're going to have to communicate the information about the potential energy to domain adjacent cells of computationally remote neighbors. So here's an example. Let's say we have 4 processes. And so we could divide up our domain like this into, like, let's say 4 sort of flat, you know, sections of the domain. And then we could further subdivide it using threading. We could subdivide it into 16 sort of domains that we're going to calculate in parallel. Right, and so, for example, at this line right here, like this cell here needs to know the value of this yellow cell here needs to know the value of this red cell right above it. So we're going to have to communicate about that, right? And this red cell needs to know this dark red cell, what the value is there. But the nice thing is those are sharing memory because they're on the same processor. They're just different threads that are sharing memory. So we don't need to directly communicate that to the next door neighbor thread, but we do need to directly communicate to our next door neighbor of the of the MPI domain. Okay, so if you think about it, this is kind of like what our communication patterns are going to look like. So on one hand, we could choose to just communicate everything between threads, right? We could communicate between just MPI processors like this. We just have all of the information from T0, T1, T2, T3, and have T0 of P0 send it to T0 of P1, right? We could do that. That's what this purple represents. You can see it's kind of like thick, representing the communication that we're going to need to do. The degree, how much information we're sending. Okay. So then if we wanted to have, basically point to point sort of communication on our mesh, then we're going to have to do a lot more communication. So we're going to have to send a little message from P0 T0 to P1 T0. We have to send a little message possibly from P0 T0 to P1 T1, because it might need the information from this grid, depending on how we're setting up our structure. Okay, so the only point I'm trying to make here with this is that the communication pattern is going to differ depending on how we decide to set up our hybrid program, and we just have to consider like what is the best way to do it. For a very an example like this one where everything, all of these mesh sizes are constant, and it's going to take a constant amount of time to calculate the value of each point, then this is probably the most straightforward, to just go ahead and just send all of the information. However, if you had something where this was like a more irregular mesh, or some mesh points are harder to calculate than others for some reason, then you might consider more asynchronous communication, like this type of a model. But for most, simple purposes, just doing the communication this way is probably the best way to do it, so you don't get yourself confused, and so you're sure that your algorithm is really going to work. Okay. So that concludes my discussion of hybrid programming. Does anybody have any questions before we move on to the next section? Okay, so we're gonna now compute pi with hybrid programming. That's gonna be our next exercise. So we will have done the OpenMP version. We will have done our collectives version, right? And so we're gonna kind of combine those into a hybrid version. So yeah, that's our next step. And then I just want to mention here, we have big bibliography here. You may notice the very first thing here is the OpenMP Common Core book, written by a certain person in this room whose name you might recognize. I actually have a signed copy in my office, not to brag. But anyway, a lot of really good resources for OpenMP. Good resources on, the OpenMP standard 6.0. And then we've got good resources on hybrid programming as well. You can check those out. And if you're terribly curious, you can talk about how to better compute pi. So like in real life, like I told you, don't use the method of darts. Use other ways, like the BBF formula is a good one. Quadrature, something like that. Programming languages usually have pi defined as a constant. And then also about random number generation. So this is actually one of my favorite topics in the whole world. So I'll just give you a brief overview of it, but there's no such thing as random numbers. Really what we're talking about is pseudo-random numbers. So you're generating a long sequence that seems random. And so a good pseudo-random number generator is gonna have a very long period. It's gonna be uniformly distributed. It's gonna be reproducible and quick and easy to compute. Now, the one that we are using is a linear congruential generator, and those tend to have a short period. This one has a period of 714,025. It is not uniformly distributed. It is known to have correlations. And actually, there was a really famous one called Randu. And Randu was used actually in the simulation of designs for the US nuclear arsenal. And you can see it has this correlation. So these are triples of what's generated by Randu. And you can see they just lie in these planes. So, but the good thing is it is reproducible and it is quick and easy to compute, but it's poor quality. So if you really want one for serial codes, I recommend the Mersenne Twister. The GSL, which is the GNU Scientific Library, includes the Mersenne Twister. Also, the Intel MKL library has a Mersenne Twister. And for parallel codes, I recommend one called Spring, which is the leading parallel pseudorandom number generator. I believe Intel MKL also has a parallel pseudorandom number generator, but I think it's like limited to, I don't know, 128 or something, different streams. I don't know. Anyway, I mean, that's fine if you're not using more than 128 parallel streams, but anyway, those are my recommendations. So that's kind of the end, but okay, so let me stop sharing here.